method I will be illustrating today is called visual multiplication, and it is referred to as such due to a lack of proof on the history regarding the name of it. So starting with the method that is most commonly used these days, so if we were to do a non-trivial multiplication by hand, we would put it in this column format, be it, 2 places or greater. So here I chose 12 times 12 for this example. It is trivial due to memorizing of multiplication tables, but it serves for a proof of concept. So if we were to do in this column format, it would progress just as so. 12 times 2 is 24, 12 times 10 is 120, summed together is 144, and then to show the distributivity behind that, we have 12 times 12, which is equivalent to 12 times 10, plus 12 times 2, which is again 120, plus 24, which is 144. So both of these are equivalent. On this right side, we have the visual multiplication method, to where these would be 10 times 10, which is 100, 2 times 10, which is 20, 2 times 10, which is 20, summed together, which would be 40, and then of course 2 times 2, which is 4, all of that summed together, which is again 144. Showing that these 2 or 3 methods are equivalent, I will now go through an example illustrating this method step by step, and then I will go through the 4 multiplicative cases. The algorithm behind this method can be simplified as rows. Represent, so we will represent each number as a series of lines representing their numerical value. We will orient them such that they are perpendicular to each other. We will sum the intersections of the resulting perpendicularity, and then we will evaluate the sums and positioning of this resulting number. The computations in these examples and scenarios will already be oriented such that you see here, and will be sped up for a respective time. So, for example, we have 6 lines here, and then we have 8 lines here, so they are perpendicular to each other, and we will count these intersections to find out what 6 times 8 is. And so, we know, since it is a fairly trivial case, that 6 times 8 is 48, and so there are 48 intersections here. Let me turn off my snap. So that is our product, and we can confirm that either using the manual method described at the beginning or with some other tool such as a calculator. So here we have a much less trivial example. So we have 26 times 38. So these two represent 20, one line for each for the value. And then we have a void here to separate our spaces, and then we have 6 lines for the ones place. And similarly, we have 3 lines going this direction to represent the 3, or to represent the tens place, which is 3, and then again a void, and then the 8 lines to represent the ones place. So using this example, I will highlight the columns. We have 1 here, 1 here, and 1 here, where this leftmost column is our greatest position. This again would be the next smallest, and the far right column will always contain our smallest place value. So starting on the left, 2 times 6, or I misspeak, 2 times 3, obviously 6. And then we have 3 times 6, which is 18, plus the 2 times 8, which is 16, And in that last column, we have 48, which we know from the previous example. I will move these. And so we will evaluate this using two separate fashions. First, we will write them in the order of the columns, where each column represents a place of the final solution. And so, as you can see, we have 6, we have 34 here, and 48. So since we're in base 10, no place can have more than 9. In other words, anything that is greater than 9 will move up. So we will take that 4 from 48 and move it up, giving us 34 plus 4, which will look something like this, and 8. Then we will move the 3 from the resulting 38 to get something like this. And so, obviously, we will end up with 9, 8, and 8, which will be equivalent to 988 if we were to put them next to each other instead of above each other. Alternatively, we can evaluate it with trailing zeros and summing each column down. So for example, we can see here that we have 6 and 2 columns behind it, so we have 600. We have the 34, and then 1 column behind that, and then we have 48. So we can sum that up fairly easily, going vertical. So in that last column, the one on the right, we get 8. In the second column, we get 8. And we get 9 in this first column, 6 plus 3. Providing us, again, with the same answer in both. So now we are moving on to cases that we saw next to the proof. So the first one is multiplication by 0. So this will be 472 multiplied by 0. Here, and in practice, I represent 0 with a squiggly line such that it stands out from the other lines. So if you did not represent 0, while in this case it would work, it does not help us when we have to hold places that have a 0. So like multiplying powers of 10. But for this example, we can compute this fairly quickly. So since anything times 0 is 0, or there are no intersections worth counting here, we know that 4 times 0 is 0, 7 times 0 is 0, and 2 times 0 is 0. Meaning that the product of this example is 0, which is proven by anything by 0 is 0. Pretty base concept. So on to the next case, we have multiplication by 1. So I have put a single line here to represent the 1 by itself. I placed it in the middle just for clarity's sake. And again, we are using the same number, 472, represented by 4 lines, a void, 7 lines, a void, and 2 lines. So each one representing each particular place. So looking at the intersections, here we have 4 intersections between each line, and here we have 7 intersections formed by each line, and here we have 2 intersections formed by each line. Again, those golden lines are just showing the columns, since they are not immediately evident while you're learning this. So if we were to put our results together, we get 472, illustrating that anything multiplied by 1 is again the initial number once more. So here the squiggly lines will come in handy with multiplication by powers of 10. Starting with rows, we can see that it's already aligned for us, as we discussed earlier, and now we just have to sum the intersections. But first I will show the columns, because for this example they definitely do not show themselves easily. So as we can see, there are certainly much more columns than we had encountered in our previous examples and cases, which is where keeping these zeros comes in handy. Because if we did not represent these zeros, we would have this singular line and series of intersections, which would only give us the 3 columns. So if we count, instead of those 3, we now have 3, 4, 5, 6, 7 columns. And then I will use the trailing zeros method for this one. So in the first column we have 1, 2, 3, 4, 5, 6 trailing zeros. In the next one we have, just to line it up, 1 less trailing zero. In the next one we have 2 less trailing zeros from the first. And of course, if we did not identify our columns, we would not know how many trailing zeros there were. But for the example's sake, we can see that this becomes 472. 1, 2, 3, 4. That is our product. Through identifying these columns, this was key. So again, the trailing zeros method works if we identify our columns beforehand. Otherwise, we can do it by orienting them, such as in example 2, where we look at each column individually. But this now brings us to multiplication by integers. And just for simplicity's sake, we are using 472, but this time it is being multiplied by 561. So, of course, the first 2 steps, represent and orient, are done for us. 4, 7, 2, void, void, 5, 6, 1, void, void, and as you can see, it creates a void all the way through the pattern. So first I will identify our columns again. It gets a bit easier with these the large voids make it much more evident, and they are not always perfectly above each other like columns are in, say, matrices. So for this, I will not use trailing zeros, and I will write them in a vertical format just to give some example between the 2 methods. So first we have 4 times 5. In that second column, we have 5 times 7 plus 4 times 6. In the third column, we have 2 times 5 plus 7 times 6 plus 4 times 1. In the fourth column, we have 2 times 6 plus 7 times 1. And in that last column, we have 2 times 1. Keeping with this, so obviously the first column will give us 20. Oh, sorry. This next one will give us 35 plus 42. This third column will give us 10 plus 42 plus 4. Fourth column gives us 12 plus 7. And obviously the last column gives us 2. Just going to move these out of the way. And I'm going to zoom out just so we can see each part. And so moving down here, so again, that first column is 20, 35 plus 42 is 59. The third column is 56. Then we have 19 and 2. There we go. And so, again, starting from the bottom, we will take the 1 from the 9 and move it up, the 5 from the 56, move it up, the 59, or sorry, the 5 from the 59 and move it up. So we have 20 plus 5. It doesn't matter if we were to move the 2 up, since that's the highest place, it really does not change anything. So making another place does not help our evaluation is essentially what happens. And then we have the 9 left over from the 59, plus the 5 from the 56, the 6 plus the 1, say one thing, do another. And then of course that 1 comes from the 19, which is left on its own, and the 2 here. And so 25, 14, 7, 9, and 2. So now you can see that we obviously have to move that 1 over, giving us 26, 4, 7, 9, 2. And then if we were to put that together in a horizontal format, we get 2, 6, 4, 7, 9, 2. This can be confirmed again by doing that manually, that multiplication of 472 and 561. It can also be done by using a tool such as, but not limited to, a calculator. So just to get that all in one screen for you. This also works with the trailing zeros, but since I had showed that on the previous example, I will not show it again. So thank you for watching and join me in this adventure of visual multiplication.